Today we're going to talk about something called torque, which is the rotational equivalent to force. The four forces shown have the same strength. Which force would be most effective in opening the door? Here we can start eliminating some of them. We know that if we push directly along the door frame, i.e. F2, it's not going to move either way. It doesn't know whether to go up or down, so the door doesn't move at all. So that's pretty good. We also know that pushing close to the hinge is less effective than pushing far away. That should be your experience. So F4 can't be equal to F1, and so it can't be the best way. On the other hand, F3 and F1 both act at the same point, and they have the same strength, so it's tempting to think that they might have the same effect. But we know that pushing the door obliquely is not going to be as good. And so we're left with that it's F1 that's going to be the most effective. It's going to open the door most easily. It should be clear that forces can cause rotations, but it's also clear that the concept of force is not enough. In addition to knowing the magnitude and direction of the force, we also need to consider its placement, where it acts, and in what direction. The rotational analog to force is something called torque, symbolized by the Greek letter tau, which is kind of a curly T. Every force generates a torque, although it's possible that the value could be 0, as we've run into many other times in the class. Also, the torque generated depends on the point of rotation that we pick. Usually it's pretty clear which point to pick, the location of the hinge or pivot or other device constraining the rotating object. We will talk about what happens if you push on something without an obvious hinge, and what really is going on with that point of rotation, and what if there is no rotation. Those will come up later. The torque is larger when the force is larger, and the torque is larger when the force is further from the pivot. Those are the first things we talked about. The torque is 0 if the force points through, or away from, or into the pivot. The torque is maximal when the force points perpendicular to the line, connecting it to the pivot. Any force can be broken into components, one along the line connecting to the pivot, which I call F parallel, and one perpendicular to that, which I call F perpendicular. Only F perpendicular exerts a torque, a non-zero torque. The torque itself has a direction, which we'll take as positive when the torque tends to rotate the object in a counterclockwise sense. In other words, in the same way as increasing angle. If the torque tends to increase the angle, then we'll call it positive. And we'll call negative the other way, or clockwise. We define the radial line as the line starting at the pivot and extending through the point where the force is applied. The angle phi is measured from the radial line to the direction of the force. So here's the radial line. Notice that we extend it if needed. Here's the force. And theta is this angle. It's important to understand it's between the extension of the radial line and the force. It's always the acute angle that's formed. And then torque is dependent on the perpendicular component of the force. Just on this one, this guy doesn't do anything. Tends to pull on the pivot, but doesn't tend to rotate the wrench. It can sometimes be easier to geometrically deal with the lengths rather than the components of the force. So we define something called the line of action as the line that contains the force extended forward and backward as need be. And we define the moment arm as the shortest distance from the pivot to the line of action. We usually denote the moment arm R perpendicular because, as we know from geometry, the shortest distance between a point and a line is along the line perpendicular to that line. So this direction. Together, these gives us 3 different expressions for torque, and we're free to pick whichever one is the most convenient. We can use that the magnitude of the torque is R times F perpendicular. We can do, that says take the components of the force and take the perpendicular component. We can also take that it's R perpendicular times F, the moment arm times F. Or we can say, let's be careful here. Sorry, there's a bit of a typo in the thing. Or we can say that it's R, the size of R times the size of F times sine of the angle between them, which your book is calling phi, so I'll also call phi. The units of torque are meter newtons, which is always written as Newton meters. It's always written that way because we don't want to think that it's millinewtons, so it's N in front of the M. These turn out, of course, to be the same units as energy, but no one ever writes joule as a unit of torque, and no one ever writes energies as units of torque, or torques as units of energy. So it's weird that we have two different things that have the same units but get different names, but that's because they don't directly translate into each other. Okay, so here's this force acting on this pivot. Draw the line of action for the force using a dashed line. The line of action, remember, is the line that contains the force. So it would be something like this. And to respect the directions, let's make it dashed. All right, something like that is the line of action. Drawn a little bit more cleanly this way. Now, given that figure, draw the moment arm for this force. Remember, the moment arm is the shortest segment that's connecting the pivot to the line, which we know will be perpendicular. So something like that. All right, draw the line of action for each force using the corresponding color, and draw the line of action as a dashed line. So our purple one is going to be something like extend it backward and forward, but dash it. The green one would be extend backward and forward, but dash it. And the blue one would be extend the line forward and backward, so this way, and also sort of out that way, and again, make it a dash. So something like that. Again, somewhat more cleanly, something along these lines. You might have already noticed there's something sort of special about the blue one, and we're about to talk about it. Now we want to draw the moment arm for each force using its corresponding color. So the purple one, we start at the pivot and go perpendicular to the purple line. So that's the moment arm for the purple one. For the green one, we go perpendicular, but notice that perpendicular is along the actual device. That's not a big deal, but interesting notice. And then the blue one, well, the blue one's kind of weird. The perpendicular distance between the pivot and the line of action is 0 because the blue line went through, the blue line of action goes through the pivot point. So its moment arm is 0. I can't really even draw it because it has no length. The key thing about that, of course, is that because it has no length, the torque, which, as you might remember, is tau is r perpendicular times f, is going to be 0 for that force. In fact, any force whose line of action passes through the pivot is going to have a torque of 0. Any line that points through or acts at the pivot is going to have a torque of 0. And those so-called tensor forces will become really important for our analysis. All right, here we have a top door view of a door, and we're asked to find the torque in Newton meters. So go ahead and do that. We might be saying that, for instance, tau is RF perpendicular. They've kind of suggested that we do that, though, with S drawn. So then we have to find F perpendicular. We do that by doing our triangles and finding this side of a triangle has a hypotenuse of 240. But we have to be careful because, well, I guess not. We can say this, and that's F perpendicular. So F perpendicular over 240, which is the adjacent over the hypotenuse, is the cosine of 20. So bringing that down here, F perpendicular is 240 newtons times the cosine of 20 degrees, whose value you need to find. Notice an important thing as a student, that you are sometimes going to be using radians and sometimes you'll be using degrees, so you need to make sure your calculator is in the correct mode. Or if you're using something like TI, you can tell it within the actual function to use degrees or radians, which is a little bit more annoying. But so 255 newtons. So tau then is 0.75 meters times 225.5 newtons, which rounded to the right number of places, looks like it's 169. Actually, it's probably more like 170, really, because I think we only have 2 digits here. So something like 170. Now, you might remember we also had tau equals RF sine of the angle, but we have to be careful because not this angle, but rather this angle, because that's the angle phi between the radial line and the force. So we have to end up using sine of 70, which is the same as cosine 20, so we get the same answer. All right, so they ask us here, they say compute tau around point P. So we're going to hold this board or whatever in place right here and spin it around. Circle in blue the force or forces that exert the greatest torque, and red the force or forces that exert the least torque in magnitude. We can begin by getting the least one because we can look right away that if we look at A, its line of action will look something like this. In other words, A is pointing away from but through the pivot, which means it exerts 0 torque, which must be the least. So that's it for red. For the other guys, we're going to have to actually find their lines of action and see what comes out. Remember that tau is going to be r perpendicular times f, but the f's are all the same, so tau is going to follow the same order as r perpendicular. We just need to find how big the moment arms are. So let's work backwards. Let's take D. D's line of action is like this, so D's moment arm is 2. C's line of action is this, so its moment arm is also 2. So they're tied. Wherever they fall in the ranking, they're tied. And B's line of action is this, so its moment arm is this length, but we can see from the triangle that that length is 2 root 2. It's the largest, so B wins. As a reminder, a torque that tends to rotate the object in a counterclockwise direction is positive, while a torque that tends to rotate the object in a clockwise direction is negative. And for these, you should pretend just for the moment it's the only force acting. It was the only thing going on. Sometimes you can also just say, hey, where is the moment arm, and what is it doing as if the moment arm were the stick that it were applied to, and that would also work. All right, 3 forces of the same magnitude are applied to a rectangle as shown. Forces F1 and F2 act at a 45-degree line to the 40 vertical, and F3 is horizontal. For each force, indicate whether the torque around the axis to the given point would be clockwise, or anti-clockwise, or 0, where anti-clockwise is a physicist's way of saying counterclockwise. For each of them, we'll need to do, I think the easiest thing is to draw a moment arm. So let's take, we'll take point A first. The line that, actually, we can just draw the line of actions first. So let's draw our lines of action for each of our forces. So blue is 1, and green is 2, and purple is 3. And now what I want to do is start drawing moment arms, which is the shortest distance from this from the pivot point to the line of action. So for instance, for point A, for the blue force, it's that. And we can see that if you were to pull on this this thing, as if this were a stick and you pulled on it, it would spin that way, which is clockwise. On the other hand, if we look here, the moment arm for green is 0 because it passes through point A, so it wouldn't tend to move it either way. And then if we look at point A and F3, this is their moment arm. And if you again think if I had F3 pull on that arm, it would sort of swing it that way, which is anti-clockwise. All right, let's clean up and redo those. Let's restore the lines of action. So here is the line of action for 1, and here is the line of action for 2, and the line of action for 3. But now we're going to rotate around point B, which is this point. So we draw a different set of moment arms. The moment arm between F1 and B is this, and we see again that's going to be in the clockwise direction. The moment arm for F2, though, is going to be this, and that's going to be in the, well, if we pushed with F2, it would spin that way. That's anti-clockwise. And we see that for 3, the line of action passes through point B, so we know that it has 0 torque. And then for point C, all of the lines of action go through point C. So we get 0 torque for F3, and 0 torque for F2, and 0 torque for F1. At point C, it would not rotate if fixed at point C. All right, the net torque is the sum of the torques due to the applied forces. Duh, but worth knowing. Tau net is tau 1 plus tau 2 plus tau 3 and so on, which we often write as sigma f. Notice that some of these torques might be 0, and that's fine. For instance, the axle force in this gear chain, we have the chain pulls this way, and the chain also wants to pull back that way, but there's you might be pushing on a pedal, but the axle, which keeps it in place, does not cause a rotation. Which third force applied on the wheel applied at point P will make the net torque 0 when we pivot around this point, not around that point? And so let's look at what we get in terms of lines of action. So the lower guy will have that line of action and that moment arm. And this guy, the angled guy, oh, wait a minute, the angled guy acts at the pivot and contributes no torque. So drops out of the problem. And then this one will have a line of action depending on each of these things, and we need to make up the opposite torque. Whatever torque the green guy does, we need to do the other way. So what kind of torque does the green guy do? Well, if I were to apply the force, this force, to this little stick of an arm, it would tend to rotate this way. All right, that tends to be a positive torque. So I'll need to have something that starts a negative torque. And we can see that this one certainly does not. Right? If I had a force like this, let's draw that in. Let's draw each of them in. So if we had this guy, that would be the line of action. This would be the pivot. That is also a clockwise force, counterclockwise force. So that's no good. Points the wrong way. In fact, we'll need something to point upward. So that means probably that D is out as well, because D points this way. Its line of action goes through the pivot. It's not going to contribute a torque, so that one's out as well. C at least points in the correct direction. How about B? Well, B goes this way, so would also tend to be a counterclockwise torque. B points in the wrong direction. It's out. So now we want to talk about A or C. And here we come back to the other idea with A and C, which is that if I put a force this way, I get the correct direction because the moment arm looks like this, which would tend to spin that way, which is the opposite way. So that's the correct direction. But then we have to worry about the size. And if we call this one F at a distance R, with a moment arm R, then the tau of that one is RF. But for the purple one, we have some force, we'll call F2, but we know that we have 1/2 the radius. Right, we're closer in. And so since I have half the radius, this has to be twice as large. So it has to be A that comes out. That one's a little subtle.